All right, let's dive into a concept that's at the very heart of computer science, hashing. It's basically the secret sauce that makes so much of our digital life feel, well, instantaneous.
I mean, think about it for a second. You grab your phone, you start to type someone's name, and boom. Before you can even blink, their contact info pops up. Your phone isn't just scrolling through a list from A to Z, it's just there. How does it do that? Well, that's the big question we're going to answer today.
So, to really get how amazing this is, we've got to understand the old school ways of doing things. If your contacts were just one big, messy, unsorted list, your phone would have to check every single one by one. We call that proportional to n, where n is, how many contacts you have. The more friends you have, the slower it gets. Now, if the list is sorted alphabetically, we can be a lot smarter. We can use something called a binary search. That's proportional to log n, and yeah, that is way, way faster, but it's still not instant. And for the longest time, log n was pretty much considered the best you could possibly do. This wasn't just a practical thing, it was a hard, theoretical speed limit, all based on a really fundamental idea about how computers are supposed to find stuff. That big idea is called the comparison model. Here's a way to think about it. Imagine all your data is locked away inside these identical, sealed black boxes. You have no idea what's in them. The only tool you're given is a basic scale. You can pick up any two boxes and ask, okay, is this one bigger than that one, or are they the same? That's it. You can't peek inside, you can only compare. And all the classic search algorithms, they all have to play by these rules. So every single step in your search looks just like this. You make one comparison. Based on the answer you get, yes or no, true or false, you get to rule out a whole bunch of possibilities, and you follow a new path. It basically builds this decision tree, where every question you ask cuts your problem in half.
And that right there is why that speed limit exists. See, if you have n different items, any decision tree that can tell them all apart has to be at least log n levels deep. What that really means is, in the worst-case scenario, you're guaranteed to ask at least log n questions to find what you're looking for. For a long time, this seemed like an unbreakable wall.
Okay, so if the bottleneck is having to compare things over and over, how do we get around that? The answer, it turns out, is to kind of cheat. We need to figure out a way to get the information we need without making any comparisons at all. And here is that brilliant cheat, the direct access array. The idea itself is almost laughably simple. Just forget about comparing stuff. If you have an item and its key is, say, the number 42, you just stick it in an array at position number 42. No searching necessary. You just go right to it. And the performance you get from this is just, wow, it's unbelievable. You want to find the item with key 42? You just look at index 42. That's one step. We call that constant time. You want to add something? One step. Delete something? One step. We've totally blown past that log n speed limit. It seems perfect, right? So what's the catch? Because, oh yeah, there is a catch. And it is a huge one. Let's make this real with an example. Imagine you want to set up a directory for 400 students, and you're going to use their 9-digit student ID number as the key for your fancy new direct access array. Here it is. This is the fatal flaw. To store a student whose ID number is something like 987654321, you would need an array that has at least that many slots. So to handle all possible 9-digit IDs, you'd need an array with 1 billion positions, just to store 400 people. You'd end up with this impossibly massive, almost entirely empty array. The space requirement is just astronomical. So that's the real problem, right? We have this amazing idea for speed, but it's a complete disaster when it comes to space. The real challenge is finding a way to get the best of both worlds. How do we map these huge, clunky keys into a small, normal-sized array? And this is where the hero of our story finally makes its entrance, the hash function. A hash function is just a really clever bit of math that takes a key from that huge universe, like all those 9-digit student IDs, and it hashes it or squishes it down into a small, predictable index in an array we can actually afford to create. So the whole process is really simple. You take your big number, you run it through the hash function, and out pops a little number. And that little number is the spot in the array where you're going to store your data. So instead of needing a billion slots, maybe now you only need, say, 500. But solving one problem creates a new one. I mean, if you're squishing a billion possible keys down into only 500 slots, it's pretty much guaranteed that sooner or later, two different keys are going to land on the exact same spot. What do you do then?
This is what's known as a collision, and it's really the central challenge you have to solve when you're dealing with hashing. If student A and student B both get hashed to index 42, you can't just overwrite student A's data with student B's. That's a big problem.
Well, the most popular solution is actually really elegant and simple. It's called chaining. The idea is, instead of storing the actual student's info at index 42, you just store the start of a list. When the first student hashes to 42, you add them to that list. When a second student also hashes to 42, no problem. You just add them to the end of the same list. So now, every slot in our array can actually hold a whole bunch of items.
Okay, but this should lead to a kind of scary thought. If I just pick one single hash function and use it all the time, couldn't some really clever adversary figure out how my function works? And then they could just intentionally feed me a bunch of keys that they know will all hash to the exact same spot. And just like that, my super fast hash table turns into one very long, very slow list. I'd be totally screwed, right back where I started. And this brings us to the final, absolutely brilliant twist in the story. The answer isn't to search forever for some mythical, perfect hash function that can never be beaten. No, the answer is to have a whole bunch of good hash functions. And every time your program runs, you pick one of them completely at random. Now your adversary has no idea which function you're using, so they have no way to design that worst-case attack. This whole idea has a formal name. It's called universal hashing. It's basically a family of functions that comes with a solid mathematical guarantee. That guarantee says, if you pick any function from this family at random, the chance that any two keys you care about will collide is super, super low, no more than 1 divided by the size of your array. It makes sure that, on average, everything gets spread out nice and evenly.
And that is the ultimate payoff. When you combine a reasonably sized array, a randomly chosen universal hash function, and chaining to handle those few collisions, the expected time to find, add, or delete anything becomes constant time. We did it! We achieved instant search, not by being perfect, but by being really smart about probability.
So, let's just do a quick recap of this whole journey. We started out with a theoretical speed limit. Then we smashed right through it with a simple idea that unfortunately had a massive space problem. We fixed that with a hash function, but that created a new problem with collisions. And finally, we solved the whole thing with a clever mix of chaining and, the secret ingredient, randomness. And that really leaves us with one last big thought. We used randomness to beat a potential worst-case scenario and guarantee incredible performance on average. It really makes you wonder, doesn't it? If this one simple trick of being random can solve a problem that once felt impossible, what other giant challenges out there, in computing or even beyond, could we unlock just by embracing a little bit of chance?